Uh, I almost escaped. So, so I started by saying this morning I listened to part of the Tel Aviv number theory seminar via Zoom, of course. And the speaker was a woman from New South Wales, Australia, Alina Astafe. And she mentioned, this was not the subject of her talk, but she mentioned the question of the greatest common divisor of the numbers 2 to the n minus 1 and 3 to the n minus 1. And if I understand correctly, the question is whether this is equal to 1 infinitely often, which is a beautiful question. And now it may have been the question was whether this is not equal to 1 infinitely often, but this is the way I heard it. And I did a tiny calculation in Maple. I hope this is visible. So on this computer, I calculated the GCD of these numbers from 1 to 100,000. And then I looked at how many numbers up to, well, by 10,000, 10,000, 20,000, and so forth, the number of integers n for which this GCD was 1 divided by n. So up to 10,000, 4,000 numbers, 4,000 n have GCD equal to 1, or about 41%. Up to 20,000 is slightly less, still about 40,000. Up to 30,000, it's about 40%. Up to 40,000, 39%. It's, I mean, this ratio is decreasing, but not very, very much. It looks like about 39%. And if instead of doing the aggregate, if you look at each 10,000 range, 1 to 10,000, 10,000, 1 to 2,000, and you look at how many, what fraction of the numbers in that interval have this GCD equal to 1, it's around, it looks like it's around 39%. It's not strictly decreasing. It goes down and it jumps up a little bit. It really is very interesting. And I don't know whether, in fact, if you take the lim inf, as n goes to infinity, of the number of n less than or equal to, let's say, capital N, where this GCD, I'll call this a sub n equals 1, divided by n is 0, even. But if anyone knows anything about this question, I just found it very, very, extremely beautiful. So, okay. That's my digression.
Yeah, I agree. If this isn't beautiful, nothing is beautiful.
Sorry, I didn't hear. All right. So what I'm supposed to talk about, and will, is something having to do with Sidon sets in a couple of different settings. So if we have G, some additive abelian group or semigroup, it hardly matters, and we take a subset A of G, we take the usual H-fold sum set, so everything you can represent as a sum of H elements from the set A, not necessarily distinct. And so you can say that an element B is in HA if and only if you can write B as some sum U sub I, A sub I. So let's say A is A sub I in some set capital I, where the U sub i's are non-negative integers and summation U sub I is equal to H. And A is a Sidon set if whenever you have two representations of this sort, Ui is equal to Vi for all I. So basically there's essentially up to some permutation of the elements, if you wish, there's only one way to write in an element A, an element of the group, as a sum of H elements of the set. And so infinitely much is known about these things, of course. Usually in discrete groups or in the integers, I want to look at something like Sidon sets in fields. And as far as I know, very little has been written about this. There's a very nice paper by Filarillo and Ruja.
Mel.
Yes.
Mel, could I interrupt for a second? Are we recording this lecture today?
Yes.
Okay.
Okay.
I usually get a recording flashing thing that I'm not getting right now.
Oh, well, someone observed that when I started, I was not recording. And okay. According to my computer, it is recording. So okay. It should be okay. Anyway, Filarillo and Ruja have a paper on real and p-adic Sidon sequences. And there's very little that other than that I'm aware of. But my point of view about this is going to be slightly different. So you might like your field of rational numbers or real numbers or p-adic numbers. And I'm just going to fix a field F of characteristic 0, which has a non-trivial absolute value on it. So if you have an absolute value x, it's trivial. This means that the absolute value of x is 0 if x is 0, and 1 if x is non-zero. If your absolute value is non-trivial, then there exists some x such that the absolute value of x is not just 0 or 1. And that implies, among other things, that the field is infinite. You can't have a finite field with a non-trivial absolute value. And if you take the inf of the absolute value of x, for all x different from 0, that's equal to 0. So you can get elements of the field with arbitrarily small positive absolute values. And these are the only two facts about a field that I need. Characteristic is 0, unfortunately, and there's a non-trivial absolute value on the field. So if you don't like this, just think of the reals. They're perfectly good, or the rationals or the p-adics, whatever you like. And what I want to prove is that in a certain sense, Sidon sets are ubiquitous. So suppose we let A be a subset of the field, and let epsilon, this is going to be a sequence or epsilon sub i's indexed by I, where all the epsilons are strictly positive for all I. And so we say that the set B sub I and I, is a perturbation of A if the absolute value of AI minus BI is less than epsilon I for all I. So you have some set or some sequence in the field, you have some set of epsilons, and a perturbation of the set A is just another set where the ith element of B differs from the ith element of A in absolute value by a mostless epsilon sub I. And a theorem that I want to prove is the following. So again, F is this field of characteristic 0 with a non-trivial absolute value. So we have this sequence of elements epsilon sub I. Let's just index it by the positive integers. We have a set A. So the theorem says there exists an epsilon perturbation of A that is a Sidon set. I should have been a little bit more precise at the beginning. So let H be any positive integer. So you take any positive integer H, take any sequence of positive numbers epsilon sub I, any sequence A, there's some epsilon perturbation of A that is an H Sidon set. That is, A is a Sidon set for the H-fold sum set. Okay. So that's the theorem. And the proof is not very complicated. Proof goes as follows. We need two lemmas. So the first lemma says the following. So this is just a general fact about addition in any abelian group. So G is some additive abelian group, and let A be a subset of G that is an H Sidon set. So every element of the H-fold sum set HA has a unique representation. And let B be some other element in G. Suppose we take A and adjoin to it B. So A is a Sidon set. A union B is an H Sidon set. If and only if the H plus 1 sets A, R, comma, H of B, this is defined as follows. This is the R-fold sum set of A plus H minus R times B. This just means B added to itself H minus R times, if and only if these sets are pairwise disjoint for all R from 0 up to H. So this is a simple criterion for when you can add an element to a Sidon set and have a slightly larger Sidon set. And once you ask the question, this is the answer that just arises all by itself. You don't have to look very hard for it. The more interesting lemma that we need to prove the theorem is the following. So this is lemma 2. Let A be a finite subset of the field F. So not necessarily a Sidon set, but just a finite subset. for every A in the field and every delta greater than 0, there exists an element B in the field such that B is close to A. The absolute value of B minus A is less than delta, and the H plus 1 sets of the form we just looked at, AR sub H of B, which is defined to be the R-fold sum set plus H plus B added to itself, H minus R times our pairwise disjoint for R going from 1, 0, 1, 2 up to H. So I'm going to try to avoid proving things, but it's only in this lemma at one point in the proof we have an integer different from 0, and we need to invert it in the field F. So this is the only place where I need that the field is characteristic 0. So I know that every integer is invertible in the field. And now if you think about it, these two lemmas prove the theorem I stated. The theorem said, the first lemma said, if you have any set A, finite or infinite, countable or uncountable, any set whatsoever with no restriction on the cardinality, but it's a Sidon set, you can add an element B to the set if these R plus 1 sets are pairwise disjoint. And this theorem says if I have a finite subset, not necessarily a Sidon set, and I take any element A in the field, I can choose some B as close to A as I like with the property that these sets are pairwise disjoint. So if my finite set that I start with is a Sidon set, then I can always add an arbitrary element or something arbitrarily close to an arbitrary element of the field and get another Sidon set. So to prove the theorem, I start with this sequence A sub I. This is just some sequence or some set in F. Take the set A1. This is a Sidon set, because any set with one element is a Sidon set. So let B1 be equal to A1. So B1 minus A1 is 0. So it's less than delta for every delta, or less than epsilon for any epsilon. The absolute value of B1 minus A1 is 0, which is certainly less than epsilon 1. And then take the element A2 from A. So we know that there exists a B2 in the field with B2 minus A2 as small as we like, less than epsilon 2, and B1 union B2 is Sidon. So here we have the Sidon, so this is B1, B2. Then take this set, look at the element A3. There's an element B3 in the field as close to A3 as we like. You would join it to this and you get a Sidon set, and you continue by induction. And we're done. Yeah, that's nice. And one special case of this can be stated as follows. So let A be some countably infinite subset of your field. There exists an H Sidon set B such that A and B are asymptotically the same. The limit as I goes to infinity of the distance AI minus BI is 0. Okay, so that's the first result. Now, there is something robust about this proof because it used very little. So I want to describe two extensions of this. The first is to, instead of looking at elements of the field, we can consider H Sidon sets of vectors in the vector space Fn. And so again, F is a field of characteristic 0 with a non-trivial absolute value for vectors A and B in Fn. We just define the distance between the vectors as the sum of the distances between the coordinates. And this has all the simple properties that we need. And we can then prove the following theorem. Remember, the idea of a Sidon set makes sense in any place where you can add. So we were working in a field, now we're working in a vector space. You can add vectors. That's all that we need to be able to do. So suppose A is a set of vectors in this n-dimensional vector field over the n-dimensional vector space over this field F of characteristic 0 with a non-trivial absolute value. Take a sequence of positive numbers, epsilon greater than 0, for all I. There exists an H Sidon set of vectors such that the distance between AI and BI is less than epsilon I for all I in N. So if you have any sequence of vectors in the vector space, there is always some, you can always perturb it to get an H Sidon set of vectors. And the proof is essentially the same as the proof for elements of the field. You just do it carefully. There are two questions right now that I don't know how to answer. The first question has to do with fields of characteristic P. There's only one point that is one step in the proof of one of the lemmas where I needed characteristic 0 just to be able to divide something, and I don't know whether that's essential. Also, there's nothing inherent in the definition of a Sidon set that says it has to be finite or countably infinite. Are these theorems true for uncountably infinite sets? So I spent a few minutes trying to do some kind of, use well ordering as some kind of transfinite induction, but I couldn't make it go, and I didn't spend a lot of time trying it, but I was really sort of still puzzled by these two things. Okay. All right, let's go in one other direction. Where I want to extend slightly the idea of a Sidon set. So I want to consider a linear form in H variables, C1x1 plus C2x2 plus C sub h x sub h, with C sub I in my field, just a field. I don't care what the characteristic is. It can be characteristic P. It's perfectly okay. Let A be a subset of the field. So we say that, this is my definition, A is a Sidon set for this form, or I prefer to say, because there's fewer syllables, phi unique, if it satisfies the following condition. For all finite sequences AI, I goes from 1 to H, and AI prime, I goes from 1 to H in F. If phi of A1, A2 up to A sub H equals phi of A1 prime, A2 prime up to A sub H prime, this implies AI equals AI prime for all I going from 1 up to H. So this is my definition of a Sidon set for a linear form. And notice the following curiosity. The form, so for H greater than or equal to 2, the form phi of x1 up to x2 up to x sub h equal just the sum x1 up to h has no Sidon set A with more than one element. So the kind of Sidon sets we're used to considering are in a certain way very different from these. Because if you take the obvious world's simplest linear form, just the sum x1 up to xh, it has no Sidon set, because We don't allow any kind of permutation here. This is a very, very rigid definition. So not every linear form has a Sidon set. And before we start trying to prove the existence of Sidon sets for a form, we ought to know if it's even possible to have one. So there is at least one very simple obstruction to a linear form having a Sidon set. I should make one sort of completely stupid observation. If you have a form, no matter what the form is, every set with exactly one element is a Sidon set for the form, because there's no other choice. You just have one element. So the question is whether for a form you can have a Sidon set with two elements or more than two elements. So let me just write down my form again. V of x1, x2 up to x sub h is c1 x1 plus c2 x2 plus c sub h x sub h. So what is an obstruction to the existence of a Sidon set? All right, well, here is one. Suppose there exist disjoint subsets I1 and I2 of 1 up to h. Of course, you could take I1 and I2 both to be the empty set, which is not too exciting for us. So maybe one of them is the empty set, but with I1 and I2, not both empty. So suppose you have disjoint subsets of the integers from 1 up to h, not both empty, such that if you sum the CIs for I in the set I1, and you sum the CIs for I in the set I2, they're equal. And let J be the complement of I1 union I2, so that's everything in the set from 1 up to h except what's in I1 and I2. And let A be any set with at least two elements. So choose U, V, and W in A with U different from V. If there are only two elements, those are the two. W can be U or V, it doesn't matter. But U is different from V. And suppose we define AI. I'm going to define H numbers, A1 up to A sub H. AI is going to be U if I is in I1, V if I is in I2, and W if I is in J. So these three sets partition 1 through H. So I've covered all I's from 1 up to H. And I want to define AI prime similarly, except I let AI prime be V if I is in I1, U if I is in I2, and W if I is in J. So I have these two different H tuples of elements of A, and I can do the following calculation. Let me evaluate phi at A1 up to A sub H. This is summation CIAI. It goes from 1 up to H. But I can divide this set from 1 to H up into 3 pieces. This is all the i's in I1 plus all the i's in I2 plus all the i's in J. So I have CIAI, CIAI, CIAI. But for I and I1, these are all equal to U. So this is U summation I and I1, A sub I. For I and I2, all the AIs are equal to V. So this is V summation I and I2. Sorry, this is C, C sub I. And for I and J, all the AIs are equal to W. But the condition on the form was that the sum of the C's in I1 equals the sum of the C's in I2. So this is U times summation I in I2 C sub I plus V times summation I in I2, I in I1 C sub I plus W summation I in J C sub I. Let me just write this in the opposite way. This is summation I in I1 C sub I. And for I in I1, V is equal to AI prime. And similarly, for I in I2, AI prime is equal to U. And for I in J, AI prime is equal to W. So this is phi of A1 prime up to A sub H prime. So this is equal to this. But A1 up to A sub H is different from A1 prime up to A sub H prime. So not a phi Sidon set. So if our linear form has this property that some subset of the coefficients, the sum of a subset of the coefficients is equal to the sum of a different set of coefficients, no Sidon set could possibly exist. And it turns out that this simple obstruction is the only obstruction. So the theorem that allows us to start the subject is as follows. That F be a field with a non-trivial absolute value. The following are equivalent. Let phi summation CIXI, I goes from 1 up to H, be a linear form with coefficients in F. So what are equivalent? There exists a Sidon set for phi Sidon set A for phi with more than one element. There exists an infinite Sidon set for phi, and the linear form phi has what I called property n for none. So property n says the following. There do not exist disjoint subsets I1 and I2 from 1 up to H, not both empty, such that summation C sub I and I1 equals summation C sub I and I2. So this was the obstruction to having a Sidon set. It turns out it's the only obstruction. So for any linear form which has no relation of this sort among its coefficients, there always exist infinite Sidon sets. And once we know that, we can use essentially the same proof. As I said, it's quite robust. It doesn't use a lot. That we did for ordinary Sidon sets. And we can prove the following. That phi be a linear form that has this property n. That means no relations among the subset sums of the set of coefficients. That epsilon I be some sequence, some set of positive real numbers. That A be any sequence of elements of the field, then there exists an epsilon perturbation B of A. That means that B sub I minus A sub I in absolute value is less than epsilon I for all I. That is a Sidon set for the linear form. So once you have a linear form for which a Sidon set can possibly exist, then every countably infinite subset of the field has a perturbation or is asymptotically equivalent to a Sidon set for the form. That's the theorem. And I call this theorem K. Theorem K plus 1 would just be the observation that this extends to vectors in Fn. So you can take your linear form, it operates on vectors as well as on scalars, and you get an analogous result. And just make one final observation. The beloved form b of x1 up to xh equal x1 plus x2 plus xh. It fails property n, of course. We already saw it doesn't have a Sidon set in this sense because the coefficients are all ones. So C1 is equal to 1, C2 is equal to 1, and the equation C1 equals C2 violates condition n. So, yeah. Okay. That's the story. I quit for the day. Thank you all very much. Happy to answer questions or hear pejorative comments. Let me get out of this.
Thank you, Mel. Yeah, so one thing that a lot of people consider the weak Sidon sets, where you insist that the variables are distinct. Right? It's like a plus b equals c plus d, where a is less than b and c is less than d. In that case, your trick for showing that these certain linear forms don't have Sidon sets, that doesn't quite work through, right? If you need the variables to be
Right. Well, but I don't have an order. Right. This is just a purely
yeah, well,
right.
It's just about distinctness, not really about order.
Oh, sorry. So these sets that I construct, right, wait a minute.
Yes, I'm not really sure what my question or the comment even is really. Just that it's not clear if you give me a form and we change the definition of the Sidon set for phi to be for distinct inputs. If there is a Sidon set, even in these cases where you have repetitions.
Yeah. So the answer is I don't know. I have to think about that. I haven't thought about it. And the question is, yeah. So the answer is I don't know. The question is, if I have a form that satisfies this property n, and I take, well, first of all, whether property n is sufficient to prove the existence of, well, sorry. So the Sidon sets I construct are certainly Sidon sets in your sense, because H tuples are distinct. So, so in particular, if you have two H tuples whose coordinates are distinct, then they have to be the same. So a Sidon set, in my sense, satisfies your somewhat weaker condition. Right? That is, well, so I'm looking. So my condition for a set to be Sidon with respect to a linear form is that for every pair of H tuples, A1 up to AH and A1 prime up to AH prime, it's that for which on which the form takes equal values, the H tuples are coordinate wise equal. And you're saying, well, we don't have to look at all H tuples. We only have to look at H tuples with distinct coordinates. So my sequences satisfy that property. I mean, you just restrict, you have fewer conditions that have to be satisfied.
Yeah, so So if you have the form whose coefficients are 1, 2, 3, for example,
Yeah, that fails
uh,
because 1 + 2 = 3.
it fails, but only if you're allowing inputs to these forms where you have repeated. Right? It's
Well,
AA. If you substitute in AAB or BBA, you get the same thing, but you have to have that repetition to make that particular thing work.
yeah, I don't know. I mean,
Yeah.
the way I proved the necessity of this condition N was just I used the same coordinate multiple times, but I don't know whether I could have gotten the same result by figuring a clever way to use pairwise distinct coordinates.
Okay.
But you're the expert on. I mean, I rely on you for an encyclopedic knowledge of Sidon sets. So, other than this paper of Javier Filarulo and Ruja, do you know anyone else who's looked at Sidon sets for reals or p-adics or in any other continuous case?
Oh, not really, not in a constructive sense, right? You can do random stuff, but
Yeah.
And there is some literature out there for Sidon sets of binary vectors. So that's again F2 to the n. And there are some results on how what proportion of the 2 to the n points you can take for that. But I don't even know that. I don't think I've seen anything in like F3 to the n even.
Right.
It's really an untapped field.
Let's screw it up before it starts.